We're back again with the mean value theorem in a practical application. This problem I particularly like because I'm a physics major and I like math. So it's nice to see ways in which math can be applied to real life scenarios. So this problem is 4.2, section 4.2, problem number 9. And it claims that there is a sea vessel that has traveled, okay, here's the key thing, it has traveled 198 sea miles in 22 hours. Alright, so we know, if I wanted to graph this, I would normally put x as the time, so x is in hours, and y is in sea miles. Well, we know that overall, this vessel traveled 128 sea miles, so there's 128 sea miles, and it did that in 22 hours, so here's 22 hours. And where 22 hours intersects 128 sea miles, we're going to put an ordered pair there. That's going to be labeled 22 for the 22 hours in the x coordinate, and 198 for 198 sea miles in the y coordinate. And so this is the point that we're interested in, and we're assuming that we start at 0, 0. Because remember, we are referencing that this vessel traveled 198 sea miles in 22 hours. That means we have to start at 0, 0. That doesn't mean the boat left the dock at 0, 0. That just means that from the start of when they started measuring this, we're going to treat this as 0, 0. And so the idea is that there are many ways that you could take a boat and make it 198 sea miles in 22 hours. In fact, there's infinitely many functions that could model that. And to represent that, I have these different blue lines here. I've drawn 3 of them to show that, for example, the boat could be going really fast, then go really slow, and then go really fast again. Right? Because the slope of a displacement graph, which is distance per time, the slope represents speed. Right? So how fast things are going depends on how steep the slope is. A boat could start out really slow and then finish the race really fast. Or it could go a pretty constant speed and then slow down right at the end. So there are infinitely many ways that this can be attained, as you can see by these 3 example functions. But there is only one secant line, right? So the secant line is drawing from our first ordered pair where we started 0, 0, 0 time, 0 distance, and drawing a linear line from there to our finish line, which is at 22 hours and 198 sea miles. Now, the mean value theorem states that if you go from this point to that point with a function, and that function is continuous, so the function must be continuous from a to b. In this case, a is 0, because that's our first x, and b is 22, because that's our last x. And we must include 0 and 22 in that continuity. So it must be continuous. And there's an argument to be made for this in reality. So how could it not be continuous, right? A boat is sailing, right? It can't disappear from one area and reappear in another area. So if we saw like a piecewise function for this, we would know it's not the reality that we know and love. So we do know that it is continuous on this interval, including the endpoints, because we've never seen a boat behave in a way that's not continuous, or anything else for that matter, in classical physics. So the next thing we need to look for is from 0 to 22, not including 0 and 22, is this function differentiable? So these are the 2 big criterion for the mean value theorem. Now, we don't have to include 0 or 22 in our differentiability, and the reason why is because we don't know what happened before they started the clock, and we certainly don't know what happened after they stopped the clock. So because there's no right-hand and left-hand limit at the endpoints, we cannot have a true derivative at the endpoints, but that's not a problem because we do know that if we extended in time and looked outside of our time range, that the lines would be continuous because and differentiable, because once again, boats can't disappear from here and reappear there, and they also can't instantly change directions, which would be non-differentiable. So you can't have a boat going that way and then in an instant go this way at the same speed. That's just not possible in the physical world. And so we know that in a real world, continuity and differentiability are practically guaranteed in classical mechanics. And so the key here is that because of this, the mean value theorem tells us that for every single one of these possible curves, at minimum, there is one point that has the same slope as the secant line. Or in this case, one point on every one of these functions that's going to have the same speed. Because remember, slope for a time versus displacement graph is going to be speed. So you'll notice here on this line that I drew, there's definitely one point on this possible path that agrees that we will have the same slope, the same speed as the secant line. And on this possible graph, we see the same thing. And on this one, we actually have two of them. We've got one like there, and then we've got one right there. But the point is that at minimum, you will have one point where you will be traveling the same speed as the secant line. And the speed of the secant line is 198 c-miles per 22 hours. And if we divide that, so 198 per 22 hours, that's 9 c-miles per hour. So that is our speed, is 9 c-miles per hour. And so we can prove using the mean value theorem that every single possible path, at some point, the boat must be traveling at 9 c-miles per hour. Because that's what the secant line represents, is 9 c-miles per hour. And so for every possible path the boat could take, there must at least be one time at which it is traveling at 9 c-miles per hour. And that is the whole point of this problem is applying this mean value theorem to reality, in which it can be very useful. And so I hope this video was helpful, and I'll see you next time.